to our Statics with Applications series. Today we are discussing centroids, and we're going to start off by defining what we mean by a centroid. So a centroid is the geometric center of an object. Now, they are useful for many situations in statics and in courses that you'll take beyond this one, including the analysis of distributed loads, bending of beams, torsion, and there's also a couple of related topics that are calculated very similarly to the way that we'll calculate a centroid, and those are the center of gravity, and the center of mass. Okay, so you may not have heard of a centroid before, but most of you have probably heard of the center of gravity, and that's the average location of an object's weight. So average location of an object's weight, and then very similarly, the center of mass is the average location of, you guessed it, the mass of the object. Okay, and in many engineering situations, these three locations are all at the same point. So you'll hear them used interchangeably very often, but they do have three separate, more precise meanings. So we will subconsciously use the centroid for many things in life, thinking about balancing just when you're standing up. If you lean too far forward, then you move your center of gravity out of alignment with the support of your feet, and you tend to feel like you're going to fall over. If you are in the gym and you're doing squats, many people will take their arms and subconsciously put them out in front of them as they go down, because the center of mass of their body is changing. Your hips have a lot of mass as they go back. You subconsciously want to balance that weight going back with another weight going forward, and that weight going forward being the weight of your arms. So you probably have a good intuition about centroids and centers of gravity based on your own life experience, but we are going to learn how to locate these centers and centroids more precisely using some math. So let's get started with the first math concept we need to know to be able to calculate centroids or centers of gravity and mass, and that is the concept of a weighted average. Now, I'm sure already know how to find an average of several numbers by adding them together. So for example, the average of 10, 12, 15, and 20, if I wanted to find the average of this set of numbers, let's say this set is X, I want to find the average. We often denote that with a little bar over the top. So X bar is going to be the sum of all of the numbers in your set divided by the total number of them, which is 4 in this case. So let's quickly add that up. 10 plus 12 plus 15 plus 20 divided by 4 is 14.25. Okay, so that's a regular average, not a weighted average. Now, more generally, if we want to define an average for any set of numbers with any number of elements in that set, then we can write a formula for that. It is 1 over n times the sum from I equals 1 to n of xi, which is also equal to x1 plus x2 dot 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 plus xn over n. Okay, those are the same thing, just slightly different notation. And this is called the arithmetic mean. So maybe let's write that here so that we're clear. This is the arithmetic mean or arithmetic average. So each number, when we're calculating an arithmetic mean, has an equal weight or an equal importance. But now for a weighted average, some numbers have more importance than others. So a classic example that you can think of for a weighted mean is your grade in this class, right? We use a weighted average to calculate your final grade. So generally, a weighted average, the formula is going to be the sum of the individual components times the weights of those individual components divided by the sum of the weights. Okay, so let's do a quick example. We have, let's just use the weights for this class. So we have lecture quizzes, which are worth 15% of your grade. We have in-class quizzes, which are worth 10% of your grade. And we have 3 exams, so each of them is worth 25%. And the final. Okay, actually move this down here. Okay, so these are the weights for grades in this class. So now let's say that you didn't do so hot on the first exam. Maybe you got a 60. And you got, let's say you're gonna do much better on the second exam. You're gonna get an 80. And let's say you've been keeping up with the lecture quizzes, so you've got maybe an 80 average on lecture quizzes. But maybe you struggle with the in-class quizzes. Let's say that your average is maybe a 70 on the in-class quizzes. And the question is, what do you need on the final exam to get a 70. Overall score in the class. Okay, so for this example, we have a set of grades that are, let's do them in order as we've listed them on the left there. So we've got an 80 on the lecture quizzes, 70 on the in-class quizzes, 60 on exam 1, 80 on exam 2, and then we have some final grade that we're solving for. And our weight factors, those are the WIs. We've got 15% for the lecture quizzes, 10% for the in-class quizzes, and then 25 for each of the exams. Okay, and we'd like for our weighted average to be 70. So my weighted average needs to be 70, and that needs to equal the sum of each of my xi components times their weights. So 80 times 0.15 plus 70 times 0.1 plus 60 times 0.25 plus 80 times 0.25 plus my final grade times 0.25. And all of that divided by the sum of the weights, which is just 1 in this case, right? The sum of our weights is 0.25 times 3. We've got 3 of those. Plus 0.15 plus 0.1 is 1. Okay, so this is an equation with one variable in it, so I can solve it for the final grade. So let's do that. 80 times 0.15 plus 70 times 0.1 plus 60 times 0.25 plus 80 times 0.25. So all that stuff is equal to 54 plus 0.25 times my final grade. So 70 minus 54, 16 divided by 0.25. So in order to pass the class, I need to get a 64 on the final. Okay, so if you didn't know how to calculate what you need for the final exam, you can come back and take a look at this later on in the course after we've taken our second exam and finished up all of our quizzes. Okay, now we are going to use this math to calculate center of mass, center of gravity, and centroids. So let's start with the center of gravity, because this is something that we have already used a little bit in this class. Maybe we didn't call it center of gravity, but what we did is we've always taken the weight of an object to act at a point at its center. So let's just write that out. So center of gravity, which from now on I'm just going to abbreviate as CG. It is the point where all of an object's weight can be concentrated and still have the same external effect. On the body. Okay, so this point about it being an external effect, this is important. If we take all of an object's weight to be concentrated at its center of gravity, and then we try to estimate internal stresses in that body, we're not going to get the same answer as if it were evenly distributed, or distributed however it is naturally. The reason that we want to concentrate all of an object's weight at its center of gravity is for doing an external type of analysis. So this is the type of analysis that we've done so far in this class. We haven't looked at any internal forces, but I just want to highlight this point so that once you get to those classes where you're doing analysis of internal forces in bodies, you know that you can't just concentrate all the weight at the CG in those courses. But for our purposes, we can concentrate the mass or the weight of a body all at the center of gravity. And the way that we draw this, so if I have an object that's just this kind of box, then the centroid is going to be right around the middle, right at the center, assuming that this mass is evenly distributed and the density is the same. And the way that we draw the center of gravity is we make this kind of circle symbol with 4 quadrants, and then we shade in 2 of those quadrants. That's the symbol for the center of gravity. So now let's try another example. And if you're at home and you've got a pencil, you're taking notes, then I want you to try to take that pencil and balance it on your finger. And think about how you are deciding where to place it. So let me try to draw pencil. Oh. Okay, so here's our pencil. Now, how do we balance this thing? Let's think about this balancing idea as splitting the pencil in half. So let's say that we have one weight of this pencil for this first half, and another weight for the second half that is acting at their centers. We know that the weight of this first half is going to be, if I place my finger here where I've drawn my dotted line, this weight of the first half is going to be trying to rotate me counterclockwise, right? Now the weight of the second half is going to be trying to rotate me clockwise about my finger. And so the goal is to place my finger, to place the support somewhere in between these 2 weights where the moments caused by each of them is perfectly balanced. And so let's do this mathematically. Let's pick some origin point. We can say that it's just at the tip of the pen. And we'll let the distance from here to the first point be x1, and from here to the second point, this will be x2. Okay, then taking the sum of moments about O, they're both rotating clockwise about O, right? Weight 1 is rotating clockwise here. Weight 2 is still rotating clockwise, just with a bigger moment arm. And so both of them are going to be negative. So we've got negative x1 times weight 1 minus x2 times weight 2. And now what we'd like to do is create an equivalent system where we have a moment caused by the total weight, W. So the total weight, W, is weight 1 plus weight 2, acting at the centroid x bar. So let's, and now this equivalent system, let me do this in a different color. So if I have one weight here, weight 1, and this is acting at the centroid, so x bar, which this is the distance that we're trying to solve for, right? The location to put our finger. Oh, and this is not weight 1, this is just the total weight. Okay, now the moment that is caused by this equivalent system is just x bar times the total weight. So now I can just let these two things be equal to each other. It's equal to negative x1 times weight 1 minus x2 times weight 2. Oh, and this should be negative, right? Because it's still causing a clockwise moment. And then I can solve this equation for x bar. So solving for x bar, I get x1 w1 plus x2 w2 over w, which is equal to w1 plus w2. Now this looks exactly like a weighted average, doesn't it? If I go back up to my equation for a weighted average here, I've got the sum of xi times its weight divided by the sum of the weights. That is exactly what I ended up with down here. Okay, now let's try another slightly more complicated example. Let's use a seesaw and let's place some weights along this seesaw. So I'm going to put one at this end. We'll make this 40 newtons. Let's place a little one close to the center. We'll make this one 15 newtons, and then let's place medium-sized one on this end, and we'll say that that one is 25 newtons. Okay, and then I'm gonna define these distances. So let's say the distance between the first two weights is, I don't know, that looks like about 1.5 meters maybe. And then 0.5 meters. Obviously not, this is not to scale. But anyway, so here's our problem, and what we'd like to know is where to place the pin support of our seesaw. So where do we place this pin so that the seesaw is perfectly balanced? Okay, and so to do this, what we're gonna do is we're gonna take the sum of the moments. And we need to define a point that is our origin where we're going to sum the moments. And so I'm just going to pick this point right here where we have our 40 newtons acting. And that's going to be convenient. It's just going to make our calculation a little bit simpler. Can leave that there. Okay, so I'm going to call this point my origin. This is just like we did for the pencil example, where we set the origin at the tip of the pencil. For any centroid center of gravity calculation, you have to define an origin point where you're measuring all your distances from. Okay, so now let's apply our equation to find the centroid, which looks like this. Our centroid is equal to the sum of the xi's times the wi's divided by the sum of the wi's. Okay, so x1, and x is the distance from our weight to the origin. So our first weight, this 40 newtons, is acting at a distance of 0 from the origin, right? And this makes intuitive sense too when you think about the force moment that is being caused by this 40 newtons. It's sitting directly on top of our pin support, so it's not causing any rotation about the pin. So this makes our calculation a little bit simpler. We can go ahead and basically get rid of this first term since we're multiplying it by 0. Now our second weight is acting at a distance of 1.5 meters times 15 newtons. And our third weight is acting at a distance of 2 meters. Don't put 0.5 there. It's an easy mistake to make, but we are measuring the distance from our applied load to the origin again. So that's the full 2 meters, 1.5 plus 0.5. Okay, and divide that by the sum of all the weights. So that's 40 plus 15 plus 25. Okay, so let me plug this in my calculator. First term is 0. 1.5 times 15 plus 2 times 25 is 72.5, and the units are going to be newtons times meters. Remember to always keep track of your units through any calculation. And then we divide that by 40 plus 15 plus 25. So on the denominator, we've got 80 newtons. And when we look at our dimensions here, newtons is going to cancel out. We're going to be left with units of meters. So x bar is acting at a distance of 72.5 divided by 80, 0.906 meters. Okay, so that is the location that we want to place our, drag the arrow with it. This is the location that we want to place our pin support for our seesaw so that everything is perfectly balanced. So that would be about there. And one way that we can check our work, if you want to do that on an exam, always a good idea, is we can now take the sum of the moments at this point that we've placed our pin. We'll call it point P. And when we take the sum of the moments there, we should find that it's equal to 0 if everything is perfectly balanced, right? So the sum of moments at P, I've got 40 newtons acting at a distance of 0.906 meters. And then I've got 15 newtons that's trying to rotate me clockwise, so it's negative, acting at a distance of 1.5 minus the 0.906 meters. And I've got 25 newtons also trying to rotate me counterclockwise, and that is acting at a distance of 2 minus 0.906 meters. Okay, so when I do this calculation, I should get 0. So 40 times 0.906 is 36.24 Newton meters. So that's the moment caused by just this weight, this first weight, and that needs to be balanced by the moment going counterclockwise caused by those other two weights. So minus 15 times 1.5 minus 0.906 is 8.91, and minus 25 times 2 minus 0.906 is 27.35. So 36.24 minus 8.91 minus 27.35 is pretty dang close to 0. So that's a good check. And when we break it down like this, we can also start to see how much each weight is contributing. So for example, we said the first weight is causing a moment of 36.24 Newton meters all by itself. The second weight, the smaller one, is causing a relatively small moment of just 8.91 Newton meters. So it's really not doing a whole lot in comparison to the other two weights. And then the third weight over here, even though it is much less than 40 newtons, it's causing almost the same amount of moment because it is acting so far away from our pivot point. So anyway, that's a little bit of intuition and how you can validate your work as you're going through an exam. All right, so on to the next topic. We talked about center of gravity. Now let's talk about the center of mass. So the center of mass is the average location of the mass of an object. It is very closely related to the center of gravity because remember that our weight is equal to the mass times gravity, right? So if we've found the center of our weight, the center of mass is almost always going to be in that same location. As long as we can assume that our constant of gravity, or as long as we can assume that G is constant on the surface of Earth and we're working on the surface of Earth, then we can factor this out. So let me just show you a little bit more about how that works. So my center of gravity, which we've already defined, is the sum of xi times the weights divided by the sum of the weights. If I replace those weights with m times g, then my equation becomes xi mi gi divided by sum of mi gi. If I can say that these terms gi are constant, so the gravity acting on one portion of the object is the same as the gravity acting on another portion of the object, then this turns into sum of xi mi times g divided by the sum of mi times g. And I can factor out these constants from the sum and cancel them out. So it becomes the sum of xi times mi divided by the sum of mi. And this is exactly the center of mass. this is we started with the center of gravity, which I'm just going to abbreviate actually with CG. So our center of gravity is the sum of xi times the weights, and our center, or divided by the sum of the weights, and our center of mass is the sum of xi times the individual masses, mi, divided by the sum of the masses. So you can see that these two equations are very, very similar. We've just replaced the individual weights with the individual masses, and we can calculate many different centers in this same way. So if we wanted to find, say, the center of volume, we would simply replace the mi and wi with vi for volume. Okay, we could also find the center of pressure. And again, we would just replace those individual mi's, wi's, vi's with pressures, pi. Okay, so we can change our weighting factor depending on exactly what type of center we wish to solve for. And so that brings us to the topic of centroids. Centroids are a weighted average, again, like center of gravity or center of mass, but now we're weighting with a geometric property, which can be area or volume. So let's try to write a definition for centroid. I'm just looking for how your textbook defines it. Here we go. So the centroid represents the geometric center of a body. Now, the centroid may coincide with the center of mass or center of gravity if the material that your body is composed of is uniform or homogeneous. So let's think about that one. If I rewrite so I know that mass is equal to density times volume. Right? And so if I want to rewrite my equation for the center of mass, as we've defined it up here. So let me write my equation for center of mass. It's the sum of xi, mi over the sum of mi. And now let's replace mi with rho, the density of the material, times vi. Okay, and just like we did when moving from center of gravity to center of mass, if we can assume that density is constant throughout the body, then we can say that this is the same thing as xi vi times rho over the sum of vi times rho, and we can factor out those densities and cross them out. But this is only if the material is uniform. And so almost always, if not always, in this class, gravity will be constant, right? We'll be sitting on planet Earth, and gravity felt in one part of a body is the same as gravity felt in another part of the body. This is not always going to be true, the material being uniform. You can think about any object around you, for example, your pencil. Your pencil is made of wood for most of it, but the eraser is a different material. It's a rubber. And the density of wood and the density of that rubber are not going to be the same thing. Not to mention you've got the metal connecting piece that goes between the wood and the rubber, and that also has a separate density. And so for a pencil, you're not going to be able to make this assumption that the density is uniform across the full body. But the constant of gravity is the same across the full body, which means that the center of mass and the center of gravity are the same, but the centroid is going to be slightly different from those other two quantities. But now if we have a part like, let's say a steel rod, just a plain steel rod, it's made up of one material throughout, then all three quantities will be at the same location. Your center of gravity, center of mass, and centroid will all be in the same center of the body. Okay, so let's do an example to find the centroid of shape. And let's find the center of area. Of an I-beam. Okay, here's our I-beam. Let's say that these sections are each 1 inch. This is a really thick I-beam. And let's say that this middle section is 6 inches, half a foot. And this center section is also going to be 1 inch. And then let's say that each of these side sections are 3 inches. Okay, so I want to know the center, the centroid of this body, and we'll talk about a different method for doing this in the next video, but one important shortcut that you can take is take a look, is your body symmetric? Well, looking at this one, I'd say it is. It's symmetric about this center, right? It has 3 inches on the left, or 3.5 inches on the left side, 3.5 inches on the right side. So this body can be mirrored across the red dotted line that I've drawn here. And it's also symmetric about this blue dotted line, right? I've got 4 inches on top, 4 inches on bottom, and the shape is exactly the same on top and bottom. So since I have a condition of symmetry about both the vertical and horizontal center line, the centroid is going to be just at this intersection between the two axes of symmetry. And so if I just now measure, let's say that the origin is this bottom left corner, then my centroid, which has both an x and a y coordinate, is going to be equal to 3.5 in the X, 3.5 inches, and 4 inches in the Y. Okay, so that is a fairly simple one. And if you take a look all the way in the back of your book, printed on not the back cover, but the page just before the back cover, you'll find some common properties of lines and areas. On the back cover, you'll find centers of gravity for some three-dimensional shapes. And these will come in very handy in the next section when we start calculating centroids using composite parts. But for example, the back of the book tells you that for a rectangular area, or let's use the triangular area because it's a little bit less obvious. So if I have a triangular area, this is not symmetric, right, about the X and Y axes, but the back of the book tells me that the center, which they've labeled as C, is a distance of b over 3, where this X dimension is b, and it's a distance of h over 3 in the Y, where this full vertical dimension is h. Okay, so it also gives you second moments, so the area moment of inertia, and we will get to that later on in this course. And it also gives you the area of this shape, so we know that the area of a triangle is 1/2 of the base times the height. So this is a very useful table. It will come in handy very soon. And so that covers it for this video on an introduction to centers of gravity, center of mass, and the centroid. In the next video, we will talk about methods of finding centroids for more complicated shapes using a method of composite parts. And I hope this video was helpful, and I hope to see you in the next one.